Hi everyone, welcome back. In this video, I will show you how to do a Bonferroni test using R. Now, Bonferroni is one of the many post hoc tests that you can do after you do an ANOVA analysis, okay? Um, in this video, I'm going to assume, guys, two things. First, I'm going to assume that you understand what ANOVA is, and more specifically, what a one-way ANOVA is. Okay, so I'm not gonna explain any details about that. And the second assumption is that you guys know how to do a one-way ANOVA using R. Okay, so I'm not gonna get into those details. All right, perfect. Knowing that, let's start now. Before we jump into R, I want to remind you a couple of things about post hoc tests. Okay. And for that, we're going to use this example. Let's say we're doing this ANOVA where we want to see if the brand of a golf ball impacts the distance traveled by the ball. Okay. In that case, we will be testing two hypotheses. A new hypothesis that claims that the average distance traveled by all brands is the same, and versus the alternative that at least two brands yield a different mean lifetime. Now, let's say, you collect the data for this problem and you run your ANOVA, and after you run the ANOVA, you are able to reject HO and support H1. If that is the case, your conclusion will be this. Conclusion will be that at least two brands yield a different mean lifetime, okay? But think about that. That conclusion is kind of vague because you're only saying that two brands yield a different mean lifetime, but we have four brands. So we usually want to know more, like which brands are specifically different, right? So this conclusion is too vague. So if you want to know a little bit more, you need to do what is called a post hoc test. And the way you do a post hoc test is by running pairwise comparisons. In this example that we're seeing, you will need to run these six pairwise comparison that I'm listing here in this slide, okay? Now, how do you do these comparisons? Well, for example, to compare the mean distance of balls from brand one versus those from brand two, you can do a t-test, to compare two means, right? You can do a standard t-test and use an alpha significance level of 0.05. And then you can repeat the same thing to compare brand one versus brand three. T-test, standard t-test with an alpha of 0.05. And you can repeat the same procedure for each pair. The problem is, if you do that, if you use a standard t-test with alpha 0.05 for each pair, to compare each pair, the probability of type 1 error in at least one of these six comparisons is almost 0.27, almost 27%, which is huge. That's huge probability of a type 1 error, okay? So, and this is only with six comparisons. If we had more comparisons, this probability would be even higher than 0.27. So that's unacceptable. That's why we need to find alternatives to the standard t-test that better control the probability of a type 1 error. And those alternatives are the Bonferroni method, Tukey, Holmes, Duncan, and many others. And what they all do is they make adjustments so that the overall probability of type 1 error, the 0.27, so we don't get a probability like that. We get a lower probability, okay? Now, in this video, we're going to focus on the adjustments made by Bonferroni. Great. So let's jump into R. Let's jump into R, and then here I'm using actually RStudio, as you can see, and using RStudio, I created this notebook, and I'm going to run all my analysis in this notebook, all right? Now let's use this example. In this example, we want to know if the brand of the battery affect the battery lifetime. Okay, so we want to see if the factor brand influences the outcome variable lifetime. And in this case, we are comparing four brands. All right. The hypotheses that we are testing in this case are the null hypothesis is that all the brands have the same average lifetime versus H1, at least two of the four brands have a different mean lifetime. Great. This is the code that you use to run ANOVA in this case. Again, I'm not going to discuss one-way ANOVA in this video, okay? So I'm going to just run this code cell, all right? I'm going to share this notebook with you, so you're going to be able to take a look at my code. But again, this video assumes that you understand how to do a one-way ANOVA in R, okay? Um, one thing I want to say is that I have the data for this problem stored in this data frame, okay? Batteries data frame, okay? Anyway, so we run the ANOVA, and then this is the ANOVA table. Again, I'm not going to discuss the ANOVA table. I'm just going to focus directly on the p-value. And the p-value, when we compare the p-value to alpha, we can decide whether to reject HO or not. Okay. Since the p-value is 0.0136, which is less than alpha, the significance level, we reject HO and support H1, which allows us to conclude that at least two of the brands have different mean lifetimes. Now, at this point, we want to know more, like which specific brands out of the four brands have a different mean lifetime. For that, we can go ahead and do Bonferroni, okay? Before I apply Bonferroni or any post hoc test, I always like to estimate the mean lifetime for each level of the factor, okay? So I'm gonna get first the sample mean lifetime for each brand. I think this is a good practice, okay? There you go, sorted from least to highest. Okay, now Bonferroni will tell us which pairs of means are statistically different. That's what we want to know with Bonferroni, which one are statistically different. Now, first, I will show you how to apply Bonferroni step by step so that you understand how Bonferroni works. And then later, I will show you how to use a built-in function that allows us to quickly and easily apply Bonferroni. The step one, when you try to apply Bonferroni, is to find out how many pairs of sample means needs to be compared. That number is important for Bonferroni, okay? And in this case, we need to find out how many pairs of brands can be formed from four brands. And for that, we can do 4 choose 2 using this built-in function, and that is 6, okay? Now we're going to use this 6 in a step 2 to adjust the p-values. And let's read a step 2. A step 2 is very important because that's what Bonferroni does. With Bonferroni, we just run a standard t-test, okay, to compare each pair, and we adjust the p-value for that standard t-test. How? By multiplying it by the number of comparisons. So we take the p-value from the standard t-test, we multiply by 6, and that's the Bonferroni p-value, okay? So Bonferroni is making the p-values larger, and when you make the p-values larger, then you make it harder to reject HO. The larger the p-value, the harder to reject HO. So that's the way a Bonferroni controls the overall probability of type 1 error, so you don't get something like this, like 0.27, okay? As a matter of fact, if you apply Bonferroni like this, your overall probability of type 1 error, it's still 0.05, okay? Not 0.27, but still 0.05, okay? Now, the individual significant level is lower, okay? All right. To run a standard t-test, we need to do a few things. First, we need to compute the pool standard deviation using the data from the four brands. One easy way of doing that is from the ANOVA table, we can get the variance of the data using the four brands. And to get the variance of the data, we can look at the mean square of the residuals, that value, mean square of the residuals, okay? And if we get the square root of that, that will be the pool standard deviation. That's what I'm doing right here. From that table, I'm getting the mean square of the residuals, getting the square root. That's the pool standard deviation. And I also need the degrees of freedom of that mean square, the mean square of the residuals, which is 20, okay? To retrieve that 20, we can use the same thing, the summary table, degrees of freedom, residuals, and then we get the degrees of freedom, which is 20, okay? Now we need to run now a standard t-test for each pair, but we have a problem. We have a problem. We have a problem here, and the thing is that we cannot use the built-in function t.test. T.test allows us to run. That's a built-in function in R that allows us to run a standard t-test, but we cannot use it in this case because we need to use the specific pool standard deviation that we just computed. Okay. And the t.test function does not allow us to specify a value for the pool standard deviation. But that's okay. There is a workaround. We can define our own function. I define my own function to compute the p-value for a standard t-test. In this function, I'm just basically, entering the two samples and then specifying the pool standard deviation and the degrees of freedom as arguments. Then here, this is the test statistic for two sample t-test. That's the formula for the test statistics. And then I use the test statistic to go ahead and get the p-value, okay? And To get a p-value, what I do is the p-value is the area to the right, okay, of the upper tail value or the area to the left of the lower tail value. But I always want to focus on the lower tail value. And to do that, what I do is I take the test statistics, I get the absolute value, and then I put a negative in front of that. So that's always the lower tail value. And then I multiply that probability by 2, and that will be the p-value. All right, now we are ready to use this function. Now I'm going to use that function to apply a standard t-test for each pair, and then I'm going to multiply that p-value by 6, okay? So let's get the p-value from the standard t-test for these two brands. And here I have the data of battery lifetime for brand A, here battery lifetime for brand B, and now I'm going to apply my function, and ta-da, that's the p-value for the standard t-test. And then what I do next is I get the p-value for Bonferroni by multiplying that by 6, okay? Multiply that by 6, and that's the p-value for Bonferroni. When the p-value is above 1, like in this case, we need to round to 1 because the p-value is a probability, so it cannot be above 1. Guys, we repeat the same procedure for the other brands. This is A versus C, A data, C data. Then we apply that function again for AC, and that's the p-value for that pair. But that's the p-value for the standard t-test. So to get the Bonferroni p-value, we'll multiply by 6. There you go. That's the Bonferroni p-value. And we repeat the same thing, okay, for each pair. I'm going to share this number with you, and then you can run all of this code by yourself and check, okay? Then this is the summary table with all the p-values, okay? That's the summary table with all the p-values, and in two cases, we had to run round to 1, okay? Now, guys, as I told you, you can do all of this using a built-in function, okay? Pairwise t-test. And the only thing you need to do is to pass as arguments the data for the outcome, the data for the factor, in this case brand, and then you need to specify the adjustment method is Bonferroni, okay? And guys, sure enough, you get the same result. So you get a matrix where each cell is a p-value for a pair, okay? And notice that the p-values coincide, okay? So that's the p-value for AC, same one, that's the p-value for AD, okay? Value for AD, same p-value. It's just a slight difference because of rounding, okay? But the p-values are the same, okay? Just minor rounding differences, okay? I advise you to always use this function. So you don't need to use the step-by-step approach, okay? You can always use this function. Once you understand Bonferroni, you can always use this function, okay? The built-in function, okay? Now, what are the conclusions from Bonferroni? Because what we wanted to know was, don't forget, we wanted to find out which pairs of brands resulted in a statistically different mean lifetime, okay? So we need to arrive to a conclusion, and the conclusion is that the only p-value that is less than alpha is that one. That's the only p-value that is less than 0.05 between B and C. So therefore, according to the Bonferroni method, the only statistically significant difference is between the mean lifetimes of brands B and C, okay? That's the only significant difference. Now, what do we do with this? Because we can do something else, guys, okay? Many analysts like to do this next step. You can use this information to try, okay? It's not easy, but you can try to select the best and worst brands, okay? That process is a little bit nuanced, okay? But in this case, for sure, we can say the following. We saw that the only difference is between B and C. The only significant difference is between B and C, okay? And B is lower than C. So B is worse than C because lifetime, the lower, the worse, right? So B is worse than C. So we can claim that B is the worst brand because it was the only brand dominated by another brand. So B was the only brand to be shown as worse than another brand. So for sure, in this case, B is the worst brand. And in terms of the best brand, it's kind of, again, nuanced, difficult to say because the difference between A, D, and C is not significant. So selecting the best brand in this case requires a more nuanced analysis that I won't do in this video, okay? To avoid making it longer. But at least we can say that the worst brand is B, okay? The worst brand is B. All right, guys, so that's all for this video. I show you how to apply Bonferroni after you run an ANOVA. I did it step by step and then using a built-in function. And I hope you enjoyed, and I will see you in another video.